Welcome to the special astrobiology seminar. We're not holding them in general this quarter, but we are for our faculty candidates. And the last candidate will be 3 weeks from today, and you'll be getting notice about that. We're delighted to have Marc Kuchner here today from Goddard Space Flight Center in the Exoplanets and Stellar Astrophysics Lab there. Marc was an undergraduate at Harvard, and then got his PhD under Michael Brown, the other Mike Brown of Pluto fame, or I should say of not Pluto fame, but it's not Pluto so much. It's what's the final name? Eris, right? Fame. And then he was a postdoc at Harvard at the Center for Astrophysics, and then a Hubble Fellow at Princeton. And for the last couple of years, he's been at the Goddard Space Flight Center. He talked earlier today about optics designs that he's doing for the Terrestrial Planet Finder mission. But this afternoon, he's going to be talking about carbon planets and water planets and what Terrestrial Planet Finder might be looking for. So, take it away, Marc.
Thank you, Woody. We dim the lights. Sorry. What do you usually do?
Okay.
Okay. Very nice. Now, thank you, Woody. I had some trouble deciding on what the title of this talk should be. I wasn't sure whether I should put an S here or not for compositions. I decided in this version that instead of the composition of low-mass extrasolar planets, I should be generous with the idea that there are lots and lots of low-mass extrasolar planets out there, and so they deserve to be in the plural. At least that's what I hope the situation is. Here's where we are so far with our exoplanet inventory. We know a heck of a lot of planets around other stars. 208, 209, and this is how their masses sort out. Most of them are Jupiter mass or larger. We found a few recently that are approaching Neptune mass, and even ones that are. Yep, here's we go. There are a handful in the Neptune mass category. But when I say a low mass exoplanet, I'm interested in the objects down here and the objects down here. So Corot, you may know, is a mission that just launched in December and just saw first light last week. That's a French mission designed to find extrasolar Earth-like planets by transit survey. And we hope that Corot will be followed by Kepler, and that these two missions will shortly be turning in a decent inventory of real low-mass exoplanets that we can study in more detail. And then my talk this afternoon, which many of you were patient enough to attend, my lunch talk was about TPF, which will further add low-mass extrasolar planets that we can study. So, you probably recognize this low-mass extrasolar planet. The question that I want to ask before we start finding lots more examples of low-mass extrasolar planets is, are they all going to be like the Earth? Are they all going to be this spectacular blue-white color? Will they have different kinds of atmospheres? Will they have different kinds of internal compositions? A lot of people have been thinking about this question. What's the range of possible exoplanets that are out there? But in particular, I've been trying to think as broadly as possible about the question. So our home planet is a silicate planet. It's mostly made out of silicon and oxygen with a metal core. And of course we live here in this thin biosphere near its surface. But is it possible that there are other planets that have internal compositions that are radically different from this? How weird can it get? Can you have a planet that's made entirely out of nougat or peanut butter or some other exotic thing. And that's what this talk is about. So, and here's the story for what we think has determined the composition of our Earth. In fact, the rest of the solar system. The broad picture that we keep in the back of our minds is one that Lewis introduced in the 70s, which is that the solar system formed a gas disk, and the gas disk had a range of temperatures. The interior of the gas disk was hot, and the outer reaches of the gas disk were cold. And that the planetesimals that formed in the disk represented the chemistry appropriate to the local temperature. And there have been many people who did calculations of the chemical equilibrium composition of solar nebula material. And you learn when you do these kinds of studies that materials that condense in the hot part of a protoplanetary disk are dominantly metals, metal oxides. The equilibrium composition, the equilibrium chemistry farther out in the disk incorporates a lot of silicates, and farther out in the disk we start to condense ices and other volatile compounds. So the Earth, of course, represents some mix of things, maybe dominated by silicates and metals. That's why we have a planet made out of silicates and metals. The outer parts of the solar system, of course, have planets that incorporate more ices, water, ammonia ice, hydrate, things like that. Okay, so here is a diagram that Lauders and Fegley put together, illustrating some of the condensates that rain out as you cool a disk of material. So imagine that you had solar composition material, which sits here on this line in this diagram. And you started at high temperatures. This diagram shows some of the solids that would condense out the material. At solar carbon to oxygen ratio in this diagram, the first materials that condense out are metal oxides in this calculation, okay, at 1600 Kelvin or so. Then as you work your way down, you can start condensing silicates and whatnot. And that's an example of what Lewis and others had in mind with this picture of condensation, temperature-appropriate condensation, determining the composition of planets in the solar system. But of course, this diagram doesn't stop at solar composition. Lauders and Fegley were modeling the condensation of dust in the envelope of a giant star, where the carbon to oxygen ratio is not necessarily the same as the solar carbon to oxygen ratio. In the sun, there's about twice as much oxygen as there is carbon. But in the envelope of a giant star, which has undergone lots of nuclear processing, the carbon to oxygen ratio can be quite a bit different, can be higher than the value of a half that we see in the sun. So, many giant stars will form condensates on the right side of the diagram right here at higher carbon to oxygen ratios. And you can see from this diagram that if you move to the right and you pass this magical number of carbon equals oxygen, carbon equals oxygen abundance, that the equilibrium chemistry changes dramatically. And for higher carbon abundances, the high temperature condensates that you expect to form dust, and by extension planetesimals perhaps, are very different. The high temperature condensates are carbon-rich materials, like graphite, carbides, and other reduced minerals. So, that was a calculation for the envelopes of red giants. But do we ever see carbon-rich chemistry in protoplanetary disks that we see around other stars? do we ever see carbonaceous materials in evidence for carbon-rich materials surrounding young stars, young planetary systems? We sure do. Here are some recent spectra of T Tauri stars taken with the Spitzer Space Telescope, showing you the spectra of these young stars are full of emission from polycyclic aromatic hydrocarbons. Polycyclic aromatic hydrocarbons, of course, are also called soot. If you look at the spectrum of a lot of different astrophysical sources, these kinds of compounds. Someone once showed. I once went to a talk where someone compared the spectrum of a distant galaxy to the spectrum of the exhaust from a Volkswagen Beetle, and they were remarkably similar. So all kinds of astrophysical objects have PAHs, these very carbon-rich compounds. So T Tauri stars, which are thought to be analogs of the young sun, show signs of carbonaceous dust, just like that produced in the envelopes of long stars. Now, what happens if you take a protoplanetary disk and you sprinkle dust on the disk? The dust doesn't just sit there. The dust spirals inwards under the influence of gas drag. And as time goes by, the dust tends to pile up in the center of the disk. And that's what this model by Eaton and Chang illustrates. They started out their experiment with this surface density profile of dust grains. They weren't thinking about the composition especially. They just sprinkled some test particles on their gas disk. And they saw that as time went by, the surface density profile changed. The material that was out here moved inwards. And eventually, the surface density profile looked like this. There was an enhancement of solids in the center of the disk. So look down below in this diagram. There's my illustration of little particles of dust moving into the center of the disk. So we see T Tauri stars with evidence of carbonaceous grains, and we know physically that grains tend to pile up in the centers of planetary disks. This model was invoked in 1993 by Wood and Hashimoto, among other people, as an explanation for the formation of a particular kind of meteorite that we see. So Wood and Hashimoto calculated the chemical equilibrium state of material that was solar composition with one difference. They added an overabundance of carbonaceous grains, just like what you would expect in the center of a protoplanetary disk, where you had carbon-rich grains produced by evolved stars that have been transported to the center of the disk to create a region of the disk that's enriched in carbon-rich material. Right? So they made this diagram showing the compositions that you would expect, the equilibrium compositions that you would expect as a function of temperature. And if you think that the appropriate temperature for condensation is here around 1100 degrees, you get a bulk composition dominated by astatite and iron, which is a pretty good match for the composition of astatite chondrites, this particular kind of meteorite, rare kind of meteorite that they were trying to explain. Other people have taken this another step farther. What if we look elsewhere on this diagram? We see that depending on the temperature that you think that represents your equilibrium chemistry, you can get a variety of compositions ranging from those of astatite chondrites to even more carbon-rich bodies. Right? You could get planetesimals forming substantially out of graphite, silicon carbide, and carbon-enriched metals. So imagine a giant Amstel-type chondrite, if you like, or a giant a planet formed out of even more rich carbon-rich planetesimals, like those predicted by Wood and Hashimoto. Right? This planet might have an iron core, like the Earth, and it could have a mantle made out of carbides and other reduced minerals. The surface is probably going to be, by extension, materials that have been delivered to the surface. We think that the volatiles on the surface of the Earth represent materials that have been delivered from elsewhere in the solar system. But the bulk composition of this planet could be extremely different from that of the Earth. So, Fagley and Cameron were trying to understand the bulk composition of Mercury in the 80s, and this is one of the directions they considered. Perhaps Mercury formed in a very reduced chemical setting. They gave up on that idea because they couldn't get the density high enough. But since then, other people have thought about this possibility. Katharina Lotters suggested this model as a possibility for the core of Jupiter. Eric Gaidos thought about this concept. He was worrying about which parts of the galaxy might be suitable for life. He was thinking about galactic habitable zones. And then recently, Sarah Seeger and I did some calculations about carbon planets that I'll show you in a minute. So I was telling you that the chemistry of planet formation is all about the chemistry of the protoplanetary disk, to first approximation. One reason I've gotten excited about the possibility of carbon planets recently is related to this protoplanetary disk right here. Who's heard of this object? Okay, most of you have heard of Beta Pictoris. I'm glad. Beta Pictoris, of course, is a nearby debris disk. It's an A star, so it's a little bit more massive than the Sun. But it's a spectacular example of what is probably a protoplanetary disk in the epoch of terrestrial planet formation. And here's this beautiful image of Beta Pictoris with the advanced camera for surveys on the Hubble Space Telescope, which just broke yesterday, and I really hope they get it fixed so we can make more beautiful pictures like this. So Beta Pictoris is an example of a protoplanetary disk that's nearby that we can image easily and study in detail. Aki Roberge, a prize postdoc at Goddard, who's working with me, has just completed this inventory of the chemistry of the gas in this disk. That's the green X's in this diagram. And she's learned that the carbon to oxygen ratio in the gas in this disk is a spectacular 9:1, which is 18 times that.
Is this based on spectra?
It's based on loss of spectra. That's crazy, huh? All right, so what's going on here? Well, of course, as soon as she... What was that?
What's the density of the gas, though?
The density of the gas is pretty low, actually.
Not condensing. It's just this is the residual gas, right?
Yeah. Okay. So at first I went, wow, 9:1 carbon planets, right? But of course, there's always more to the story. This particular disk is a debris disk. The gas is very sparse, right? And it's quite possible. Probably this gas actually represents gas released in the destruction of planetesimals. So protocomets that are vaporizing gas that's released in the collisions of planetesimals. Something in this disk is carbon-rich. I don't know if it's planet-sized bodies that are carbon-rich, but this may point to carbon-rich planetesimals. And it may be that the solar system went through a phase like this, right? it may be that the proto-asteroids in the solar system were carbon-rich, and that they lost their volatiles due to a process similar to what we're seeing in Beta Pictoris. So maybe we're seeing a destruction maybe we're seeing the death of carbon in Beta Pictoris, right? Maybe when the planets are not going to incorporate this carbon, that's being gas. But also makes you think that there's something interesting going on there, and there is a possibility of carbon-rich mode of planet formation.
What's the CO ratio of Halley?
Let's read it off here. It looks pretty much close to 1.
The magnesium aluminum silicon and sulfur look low too. Does that indicate
What does that mean?
possible concentration?
I don't know. There may be a lot of interesting puzzles in this plot. There. And not only that, but there are other debris disks where we can measure gas and gas chemistry. And this can be fun trying to put together what all this means over the next few years. All right. In my last talk, I showed you some of my cartoons about different planet detection techniques. The one I want to focus on right now is transit observations. Okay, so transit observations are when you point a telescope at a star and you look for a situation where the star becomes temporarily dimmer, and you infer from that the presence of a planet that's orbiting around the star. So the Corot mission and the Kepler missions that I mentioned on the first view graph are expected to bring home lots of different candidates of transiting planets. And when we follow these up using radial velocity observations, we will probably have many examples of extrasolar Earth-like planets that we can study. And once you've found a transiting planet, you can re-observe the transiting planet with a fancier, more expensive telescope like the James Webb Space Telescope, and use the transit to take a spectrum of the planet. And this is starting to be a very exciting field of research, and the Spitzer Space Telescope has brought home several examples of measurements of colors and spectra of planets that have been detected first using the transit technique. So Sarah and I went about trying to figure out what is the spectrum of a carbon planet going to look like. So what do you see when you look at the spectrum of a transiting planet? You see its atmosphere. So here is a calculation of the composition of a planetary atmosphere. It's a chemical equilibrium calculation. So Sarah and I calculated at every different combination of pressure and temperature what is the equilibrium chemistry for a gas that has atomic composition just like that of the sun. And also on this diagram, we plotted a typical temperature-pressure profile for a Neptune mass planet, for a hot Neptune mass planet, like the kind of planet that you would see in a transit survey. So here, in the land of solar composition planets, the comfortable, boring land of solar composition planets, you can see that the entire atmosphere of the planet lies in this blue region of the diagram, where the gases are rich in water. And none of the atmosphere lies in the red diagram, which is the water-poor, carbon monoxide-rich part of the diagram. Now, if we turn up the carbon-to-oxygen ratio in the calculation, the scene changes. And most of this temperature-pressure regime is now the carbon dioxide-rich regime. And for this example temperature pressure profile, for this example hot Neptune, we see that most of the atmosphere is in a very water-poor carbon monoxide-rich regime. And the synthetic spectrum, as we go from solar composition, carbon to oxygen ratio of 0.5, to carbon-rich regime, changes dramatically. So here is the ordinary solar composition hot Neptune spectrum. It's full of these water absorption features. Here's this classic. You've probably heard of this 4-micron emission peak from from hot Jupiters. Right, there it is. When you turn up the carbon to oxygen ratio, the spectrum changes dramatically. Maybe we will start finding transiting planets that have these carbon monoxide dominated spectra, and that will be very exciting. What else can we do with transit observations? Well, if we stare very hard, we can get a spectrum, but you don't have to stare very hard at all just to get the mass and the radius of the planet. Here is a collection of mass and radius measurements for real transiting planets from a review paper by Dave Charbonneau and others. Okay, so here are all these different mass radius measurements for transiting planets. And for comparison, these folks have plotted some very simple models for the mass radius relationships of large hot planets. Their model consists of their model is a constant density model. Okay, so this is the radius that a ball with density 1 gram per cubic centimeter will have. This line here is the radius goes as cube root of mass line. You can see by comparing the mass radius measurements from transit observations to these lines that there are some surprises here. For one, a large fraction of these transiting planets are less dense on average than water, so they would float. We don't really understand yet why the density of some of these planets is so low. It defies our attempt to explain. Well, I wasn't planning to tell you all the wonderful details about models of the radii of these transiting massive planets. I want to show you only that transit observations are good at measuring masses and radii. What I'm interested in is this part of the curve down here, where we're going to reach with Kepler and Corot, the low mass, small exoplanets. So here is a more detailed calculation of the mass-radius relationships for extrasolar planets by Zapolsky and Salpeter in 1969. They made these models for the mass-radius relationships, which take into account the way that the planet becomes crushed when it gets more massive. When the planet is small, down here, the density of the planet is the same everywhere. A uniform density sphere is a good model, and the radius varies as the cube root of the mass. But then at some point, the center of the planet compresses, and that law stops applying. Now up here, the curves reach a maximum, and then the planet starts shrinking. If you added more mass onto Jupiter, if you increased its mass by a factor of 10 or so, it would start compressing, and it would even shrink. That's what Zapolsky and Salpeter predict. So, again, Sarah Seeger and I, we are working on this together. We're focusing on the Earth to super-Earth region of this diagram down here in this corner. and we try to improve on the work of Sapolsky and Salpeter. So where did Sapolsky and Salpeter go wrong? Where they went wrong is that they used a particular equation of state called the Thomas Fermi-Dirac equation of state, which really only works at high pressures. Is Mike Brown around? Okay. The Thomas Fermi-Dirac equation of state, for example, doesn't incorporate molecules. So clearly at low temperatures and low pressures, most substances exist in the form of molecules. We wanted to update this work, taking into account improved equations of state. So this diagram shows where planets in the solar system lie on the mass radius plot. And it shows you that planets are expected to have different radii based on their bulk compositions. So you can look at Jupiter and at these models and infer, just from knowing its size and mass, that it's mostly made out of hydrogen. And you can also look at Neptune or the Earth and see that they are mostly not made out of hydrogen. They lie below the pure hydrogen planet curves on this diagram. They must have some of these heavier elements incorporated in them. Can we use the same method to understand the compositions of extrasolar transiting low-mass planets? And will we find examples of planets that fill in some of these gaps on this diagram? Right? Maybe there are planets out there that are purely made out of carbon, like the ones I showed before. Maybe we will find planets that are mostly made out of iron, that are super dense down here. Maybe we'll find other exotic creatures. So, for example, water planets should be extremely low density. We have some water planets in our own solar system, right? The moons of Jupiter are probably substantially made out of water. Water ice, or some liquid water. Imagine that you had a free planet with the composition of Ganymede, right? I call that an ocean planet or a water planet. So there was Sapolsky and Salpeter's models on one end of the spectrum, where they took one simple equation of state that didn't include molecules. And then there is another extreme of modelers, which are people like Diana Valencia and Dimitar Saslov, who have been working on very detailed models for these planets. And this shows some of their work modeling the structures of water planets and a giant silicate planet. So Valencia et al. Have modeled all kinds of details. They've thrown as many details as they possibly could into these models, and they've included phase transitions. They've included attempts to understand all the different subtleties of mantle chemistry, and they've poured a lot of work into these models. But this isn't necessarily where you want to go if you're presented with an astronomical observation. Sarah and I said, well, what if someone tells us this is the mass, this is the radius of a particular planet, this is what we know about it, what can we infer from it? So instead of doing a detailed model of a single particular case, we want to understand the broad range of masses and radii.
But that work by Valencia et al. Was just starting with different compositions.
Yes.
Solar. And that's all it varied.
So Valencia et al. Assumed they started with the Earth, for example, and scaled it up. So this is a very detailed model of a
so they're changing mass also.
Of a higher mass Earth analog, right? And we say we don't know if it's an Earth analog. What can we deduce? So we actually throw out a lot of these details. People like Mike Brown spend a lot of time trying to understand the equations of state, for example, of the materials that compose the Earth. if you make a 1% error in the density for perovskite, you've just built yourself a nice tall mountain, right? So that's not a small error when you're understanding the structure of our own planet, because we can measure it very precisely. But if you're understanding an extrasolar planet and there's a 10% error bar on the radius, then it makes sense to approximate that level of detail away. Bless you. So here are the equations of internal structure that tell you the mass-radius relationship for a planet. I won't bore you with, but this is what we solve numerically. In order to solve those equations, you need to understand the behavior of the rocks that you put in the planet as you compress them. So here are some of our improved equations of state. We've taken a step beyond Thomas Fermi-Dirac equations of state, gone through the literature and used equations of state by Binet, Birch, Murnaghan, and did our best to paste them together into a improved representation of how these various minerals, from iron to silicon carbide to water, etc., compress as you put them under pressure. Right? Here is the pressure of the material. There's the density. Down here at low pressures, most planet-forming materials don't compress. If you turn up the pressure enough, they start compressing. Right? That's what's going on in this diagram. And here are some of our predictions. Unfortunately, we discovered that carbon planets are probably not distinguishable from silicate planets using transit techniques. So this diagram shows the radius-mass relationships that we predicted using our models for a variety of different compositions. The lowest radius planets, the smallest planets at a given mass, of all the different equations of state that we studied, are the iron planets. So, for example, you could imagine a planet that is all core. Mercury is a step in that direction. It's the densest planet in the solar system. It's probably the closest of any of the planets we know to being just a pure metal core. So Mercury would sit down here in this diagram. Actually, it's lower mass than Earth. It would sit down here in this diagram. So the least dense planets of all the different planets we considered are the pure water planets. We think we probably can distinguish a water planet easily from a silicate planet in transit observations. So we'll be able to use these observations to test ideas about the origin of the Earth's water, for example, and the transport of volatiles around young planetary systems. These are some 7% error bars, some error bars that we think are plausible expectations for the performance of Kepler. And this purple dot here represents the measured mass of Gliese 876b. This is a real, live, low-mass planet detected by the radial velocity survey. You may notice that these curves all have similar shapes. So I'll just show you for a second what that represents. These equations of state, as I was showing you, are flat here, and then at some point they turn up. The point where the equations of state start rising is the bulk modulus of the material. It's the pressure at which the material starts to crush. Right? And this pressure gives you a scale. A scale that you can use to solve differential equations in the problem. So we put together an analytic solution to the equations of internal structure using this scale to help us find an approximate solution. So we rescaled all the variables, blah, 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 blah. And when we do that, we discover that if you choose the appropriate variables to solve the differential equations, you can ignore this if you're not a math geek like me, that all of the mass-radius relationships collapse onto each other, and you see that they all have the same functional form. Sort of trivia. Okay, but I found it amusing. Now, back to other weird kinds of planets. You may know that the first extrasolar planets discovered were not planets around sun-like stars. They were planets around a pulsar. Here are the discovery plots showing you the signals that Alex Wolszczyn used, Wolszczyn and Frail used to distinguish, to recognize that this pulsar had planets. And why am I showing you this plot? It's because the planets around the pulsar probably formed in a protoplanetary disk that was quite different than the Solar Nebula. You might imagine that the chemistry of a disk around a pulsar would be very different from the chemistry of the Solar Nebula. Does everybody know what a pulsar is? I best say. A pulsar is a remnant of stellar evolution. If you take a very massive star and you wait until the end of its life, the star will explode catastrophically in a supernova, and then all that's left of the star after the supernova is a object called the neutron star, which is a mountain-sized ball with extremely high density. For example, if you look nearby at a nebula called the Crab Nebula, this nebula is thought to represent the remnants of a supernova explosion. In the center of that nebula, we see a neutron star. Neutron stars, the surface of a neutron star can be very exciting. It may have launched these jets, and the neutron stars can also spin rapidly, in fact. And every now and then, when the star rotates into view, when the star is rotated to the right position, the jet can intersect our line of sight, and we'll see the neutron star become brighter and fainter as the jet rotates in and out of view. So that's what a pulsar is. It's a spinning neutron star. Okay, so the timing of the pulses as a signal to indicate how far away the pulsar is along our line of sight. Right? If a pulsar emits a pulse and then jumps backwards, say under the gravitational influence of a planet, the next pulse it emits is going to take a little bit longer to get to you, because now it's farther away from you than when it emitted the first pulse. So you can measure the time when the pulses arrive, and that's an indication of motion of the pulsar along your line of sight. And Alex used this technique to infer the motion of the pulsar in response to a planetary system, which now, at latest count, has 4 planets in it. Anyway, this is the first discovery of an extrasolar planet. Oh, and these planets are quite possibly carbon planets. Another place where you might have interesting planet formation chemistry would be in a disk around a white dwarf. We often see systems of white dwarfs, systems of pairs of white dwarfs. So a white dwarf is another kind of evolved star. If a lower mass star, if you wait to the end of the life of a lower mass star, like something the mass of our sun, it eventually becomes a white dwarf. And white dwarfs sometimes come in pairs, and if the pair evolves in such a way that the two white dwarfs are very close to each other, the white dwarfs can merge. This produces a variety of interesting phenomena from another kind of supernova, ranging from another kind of supernova to other kinds of phenomena, novae and white dwarfs with disks and things like that. And a white dwarf with disk can form planets, right? Why not? I always suspect that whenever I see an astrophysical disk, there may be some kind of planets forming in a disk. A disk made out of a shredded white dwarf, like something that you might see in this binary white dwarf configuration, would be made mostly of carbon monoxide. So perhaps there are white dwarf systems out there with carbon monoxide planets. Again, it sounds like I'm telling you a fairy tale, but we've done a survey of white dwarfs with the Spitzer Space Telescope. Here's a list of some of my collaborators looking for these disks. And we've discovered at least one example of a very massive white dwarf with a disk around it. This plot shows you the spectrum that we took of this white dwarf GD362, which is one of the most massive white dwarfs. And the spectrum shows you the light emitted by the white dwarf over here. Right, that's what this line represents. And it also shows you our photometry that we took with the Spitzer Space Telescope. So it shows you that this model, consisting of a single plain white dwarf, is wrong, and that probably the white dwarf is hosting some circumstellar material that's colder than the surface of the white dwarf, probably a disk. The GD362 is special because it's one of the most massive white dwarfs, suggesting that perhaps the system was formed in a white dwarf merger. So this may be an example of a protoplanetary disk substantially made out of carbon monoxide. So here's my summary of exotic kinds of planets that you might want to think about, representing the range of carbon to oxygen ratios. It's pretty vague at the moment, but perhaps the details will be filled in as time goes by. At low carbon to oxygen ratios, we have the solar system, right, where the low mass planets here are made out of silicate. Sometimes they have water on them. The high mass planets are planets like Jupiter, substantially made out of hydrogen. The thinking is that you have a massive enough core inside a protoplanetary disk that the core will attract the hydrogen in the disk gravitationally, and all planets that are easily massive will be mostly hydrogen. So that's the story for that is commonly understood. Then we have, on the other side of the carbon to oxygen equals 1 ratio, we have carbon-rich planet formation, which may be occurring in disks around pulsars, in disks around white dwarfs. And there, you might infer from the calculations of instantite chondrite formation, perhaps you would expect to see carbon-rich planets, perhaps made out of silicon carbide, perhaps formed of graphite and other reduced chemicals. That means I have 10 minutes left, right? Then I've also suggested that perhaps there are some protoplanetary disks that are made out of carbon monoxide. And Mario Livios has written a paper about the possibility of carbon monoxide planet formation. So these would be planets that form out of gas, right, not out of solids. Gas-rich planets that form in a disk of carbon monoxide. There may be planets around white dwarfs, for example, that are carbon monoxide giants. Of course, the bottom of this diagram, I couldn't help speculating about the possibility of life on a carbon-rich planet. The life on our planet has a whole range of metabolisms, of course, but you and I get our energy by oxidizing carbon-rich material. Perhaps there will be life on carbon planets that works in a different way. Perhaps there can be life on a carbon planet that instead of generating energy through oxidation, perhaps generates energy by reduction. So, for example, if you had, we generate energy by combining oxygen with our carbon-rich food. Imagine an animal that had very oxygen-rich food and extracted abundant carbon from its surroundings to reduce it with, and use that source of energy. And that's about it. Thanks very much.
Well, I think I'll start off. You're a dynamicist also. You didn't talk about stability, length of time, once you've got a planet and so forth, which of course is important for life also. So,
right.
Are you seriously suggesting that you might have enough time in a planet that formed and exists around a white dwarf to get life going?
That's a good question. Okay. Well, so what's your opinion on how long it takes to get life going?
A few 100 million years. If you've got the right conditions.
If you've got the right conditions, right. We have several examples of disks around white dwarfs that we know. And we don't always know the ages of each particular disk, because in order to measure the age of the white dwarf, you generally need to know the distance to the white dwarf, or you need a very detailed model of its temperature and flux and all of that. So we don't always have that luxury. But we do know that on average, the kind of white dwarf that we looked at, the typical age is a giga-year. So perhaps we're looking at examples of white dwarf disks that have had 1 million years to evolve whatever kind of critters you might like.
This will certainly open up the spectrum of places to be looking at.
I think so.
No, but like another question, TPF, you talked at noon about the tremendous problems with the dynamic range you need to see the light from the planet versus the star.
Right.
The white dwarf is a much lower luminosity object. Could that be helpful?
Exactly. That should be very helpful. So, for example, in our survey of white dwarfs, we calculated that we would have enough dynamic range to see a 3 Jupiter mass planet around most of our targets. Do you know how much dynamic range it took? Not 10 to the minus 10, not 10 to the 10 contrast, 10 to the 1 contrast.
10, factor of 10. Was that at 1 AU or?
We didn't expect to resolve any of the planetary systems, so anywhere within our giant 3 arc seconds.
Other questions, comments? John?
Just the formation of a carbon-based planet, is that compatible with evolutionary water? Looking at your temperature profile as you move further towards a more carbon-based planet, could it ever have water?
I sure think it could. Why do we have water on the Earth? I chatted about this with graduate students yesterday. But you should expect the planet to receive volatiles from elsewhere in the planetary system, right? The planetesimal zones fly around, and you could easily imagine comets, asteroids, ice grains raining onto a carbon planet, as we mentioned,
So you're saying the situation is not too different from silicate plants. You're making it in a place where you don't have the water initially. It's got to get delivered through some other kind of process.
Right.
In this solar system.
The difference is, of course, that on the carbon planet you have this vast reservoir of organics. Right? You never have to. You're never short of gasoline. Right? On the Earth, we fight wars over petroleum products. Carbon planet life will fight wars over oxidizers, not reducers, right? They will fight wars over water. Okay. In India, they fight about water all the time. But, right? So, maybe that's not too different from Earth. But anyway, they will never fight over gasoline on a carbon planet.
It's only never fight over silicon carbide.
Rather than geopolitics here, we've got galactopolitics. We better not go there anymore.
Cheney world.
Yes, sir.
On your plot of the, I think it was the mass versus, the radius versus mass for different composition planets. I've got a spread of lines for different compositions, except for carbon, it seems to be a much more constrained.
Page back here.
Different line styles.
That was the main mass versus radius plot.
But this one, I didn't tell you all the details. Right. I focused on the pure planets, right? So the solid lines are pure planets. The hatched lines are planets that have mixtures of, for example, water and iron. Imagine adding an iron core to whatever you like.
Tom.
Question from Ames.
Oh. Hi, Ames.
Hi, this is Dave DeMarais here. I had a question about the thermal evolution of planets. For example, if you had a carbon-rich planet with a silicon carbide mantle, well, one question is the radioactive elements, which are so important for determining the thermal structure of silicate planets. What do you think would be the situation in a carbon-rich planet? And then a related question, of course, is that liquid and solid phases in the planet have a lot to do with plate tectonics, which of course would affect the heat flow to the surface. So even in the early phase of a planet's history, when you're accreting, you got accretionary heat. How does that get out of one of your carbon-rich planets? Have you guys thought at all about the thermal consequences of the models?
Thanks, Dave. To first order, we have purposefully ignored that, right? So we have purposefully simplified as much as we could in order to explore the range of possibilities and find analytic solutions to the equations that would tell us the range of answers. Right? So our philosophy to start out with was simplify to the point where we understand. Okay. Then, yes, of course we thought about all these other kinds of fun things. I was just having a nice conversation with Roger Buick this morning about possibilities for example, radioactive heating of the planets. When you start thinking about radioactive heat sources, though I tend to you have to stop and say, well, is that really related to the carbon planet-ness of the body, right? I mean, we're not living on a uranium planet. It's a small amount of uranium that's doing the job. So that's really sort of a higher order question compositionally. Right? It's a very important question thermally, but it's really not a first order composition question. So you can imagine a wide range of possibilities that are secondary to the observational indicators that we're trying to model, like the mass-radius relationship and the spectra. Right? What if the planet was right next to a giant star that went supernova and dumped iron-60 all over it? Okay, that could happen to a carbon planet as well as it could happen, a carbon planet system as well as it could happen to a silicon planet. That was only one of your questions. The first one was
plate tectonics.
Oh, plate tectonics. Yeah. Well, this is exactly what Roger and I were talking about earlier, do you have plate tectonics on a carbon planet? I don't know. Carbon, as you know, the plate tectonics require some lubrication, right? There could be water available to provide the lubricant. Maybe you can lubricate the plate tectonics with, butter, Crisco, some other carbon compound. I would expect that the surface of a carbon planet would be full of all kinds of organics, right? You might expect a smoggy atmosphere, a surface covered with tar, sort of like Los Angeles.
All these comments. La Brea tar pits. Richard.
How unique is the 11.3 micron feature for soot? And does it relate to the diffuse interstellar bands? What's the evidence for acidic material?
That's good. There are a variety of pH features that have been detected in astrophysical sources. Besides the 11.3 micron feature, how unique is it? There are lots of other different features. So people have seen spectacular PAH spectra from the thermal infrared down to the far infrared.
But you only have the one feature, Spitzer, I guess.
Yeah, Spitzer didn't really operate in the far infrared, but Spitzer has seen other weaker features in T-Tauri stars and Perseverance stars from 5 microns down to 20 microns. It's seen other. We're not hanging on one spectral line. If that's what you.
Yeah, that's what it kind of looked like. Yeah.
Yeah.
In this mass radius diagram, you get the radius from transits, but where do you get the mass of?
Oh, good. I didn't explain that very well. If you see a transiting planet, you know a couple of things. You know how deep the transit is, right? It tells you the cross-section of the planet compared to the cross-section of the star. And you also know the duration. You know how the duration compares to the duration of the orbit, right? So you have the frequency, and you know that the transit lasted for 1% of the orbit. It'll be a pretty long transit. But you see, that's the other observable that tells you the mass of the planet. Okay. I still haven't answered your question. You need the mass of the star, which is currently the major source of uncertainty in these mass observations. It's common that there are surprisingly few stars that we have very accurate masses for, right? But if you know approximately the mass of the star, and you know Kepler's third law, you know the timing of the duration of the transit and the period of the orbit, then you could infer the mass.
Does the mass of the planet affect that equation at all?
Yeah, it does. It's total mass is the dynamical mass, so it's sum of the masses. But more importantly, the reflex motion of the star, which you know from radial velocity measurements, tells you the mass ratio. So you know the sum of the masses and the ratio. Okay.
Time for one more. Okay, let's thank Mark again.